And it's absolutely marvelous to be here. This is not a ceremony for me. This is a ceremony for the community of scientists back in Bell Labs in those days. The materials organization, the physics organization, quantum electronics down at Homedale. That was marvelous. And I think looking back, and I'll try to make the point, I could not have done this work if I was an assistant professor somewhere trying to earn tenure. Not possible. This was completely outside what could be done in academic life in those days, and so I'm really grateful to be here. Grateful to see all my friends in the audience here today. 40 years ago we began, even more than that. 1982. As I say, I thank Bell Labs leadership for supporting this in the early stages. Bill Slichter, Kumar Patel, department heads, John Tully, Mark Cardillo, more recently, Jim Mitchell. So there are two things I can do today. One, I promised to tell a little bit about what Bell Labs was like when I showed up, because it's a long time ago and very different than what things are like now. And then, secondly, I'll talk a little bit about what we did for this work on quantum dots. Came to work in the summer of 1973, coming from active duty, actually, in the US Navy. Working as a lieutenant down at the Naval Research Lab in Washington. I had been a ROTC student, when I was an undergraduate. That was a very big institution as well. Maybe had 2,000 employees, tremendous engineering, science operation. At that time, AT&T was the national telephone monopoly, vertically integrated, meaning it did everything: manufacturing, long distance, local service, 300,000 employees across the country. This is before the invention of optical fibers, optical communications. If you wanted to call California, it was very expensive. The call was carried by microwaves across the country from one tower to the next, and many amplifiers along the way, vacuum tube amplifiers still at that time, being converted to silicon amplifiers over time. AT&T owned the telephone in your house. You only rented it from AT&T. You didn't actually own it. It was an engineering-driven organization, monopoly. Bell Labs actually had 25,000 employees in R&D when I showed up. Murray Hill, Homedale, Whippany, different locations in the Middle West. Just the research section alone of Bell Labs was 1,300 people. 300 people in materials and 250 in physics here in Murray Hill. Tremendous, tremendous intellectual operation. I showed up. Parking lot was full out there. They did not have a desk for me. Every desk in the whole complex, building 2, building 1, was occupied. So where was I going to sit? They put me upstairs on the 5th floor of building 1 in the attic, inside one of the storage cages for the old electronics. And for 3 months, I sat up there while they were trying to organize a laboratory for me. So if I think back about what happened over time, it's true in those days that I thought, I knew what was happening in academic life, and I knew what was happening internally in Bell Labs, and I thought that the most interesting projects I knew about were actually the ones inside Bell Labs rather than the ones at Berkeley and Stanford and Harvard and so forth. What was going on? Significant, there was all this development of optical communications during the time I was here, fiber optics. I'm learning how to make preforms, learning how to dope preforms to control the index of refraction. Light-emitting diodes, trying to make a diode at 1.6 microns for optical communications. Erbium amplifiers for long-distance propagation in optical fibers. All of this was worked out from scratch. I remember this tremendous hoopla over the discovery of the 77-degree semiconductors. This is maybe 1987 or something like that. Everyone in the building, and somehow, people have ideas about what the future holds, but it's often not true. We had this idea that if somebody discovered a 77-degree Kelvin superconductor, that would change the world. So it happened in 1987, did not change the world, but we worked, meaning the whole organization, worked very hard sorting out the physics of that. It's still an open question to some extent. Fractional quantum Hall effect at low temperature. Quantum Hall effect, worse work. That was a revelation because it opened up all of this new physics, correlated electron physics, as opposed to just band structure of semiconductors. That has really transformed solid-state physics since that time. Cold fusion, I remember cold fusion. There was a paper that said that you could fuse, I think, deuterium and hydrogen inside a platinum cathode. And I stopped working on quantum dots, and I spent 2 weeks working on cold fusion. Not doing the experiment, but going into the library, checking all this old literature on, the understanding of fusion processes, the Russian theorists and so forth. And at the end of that time, I concluded this has got to be wrong. It's just the old literature doesn't support it. It should not be possible. And I wanted to hang Pons and Fleischmann from the nearest tree, basically. That was what I was thinking about. Organic electronics, towards the end of my time, Bob Ludis organized that, pentacene as a conductor and all of that. These are the ideas we investigated in those days. But we were working the whole time under some kind of worry. The antitrust suit was filed, I think, in '74. Break up the Bell system in '84. Western Electric was split from AT&T in '96. And during the latter part of this time, I was always coming to work thinking, this cannot last. I have to do something significant today. Because we could see trouble. I could see trouble. My colleagues could see trouble. Tim Harris could see trouble, coming down the road. Bill Baker said, if the antitrust suit is successful, then Bell Labs will just fade away. And he was right. He was right in those days. So I left for Columbia in 1996. So this is a slide of the miniaturization of silicon, which has been the driving force for the industry ever since 1970. And this slide comes from about the year 2003, when the working on a 90 nanometer pitch scale in photolithography. And they were trying to project forward from 2003. We'd get smaller sizes, and then they had speculation, maybe you can make a transistor someday from carbon nanotube or something like that, not knowing what the future would hold. We're now in 2023. The design rule is 5 nanometers, or I think maybe 3 nanometers, coming down from this number. 114 billion transistors on one Apple chip. That's absolutely mind-boggling. You cannot imagine that. How can human beings organize 114 billion transistors to make a purposeful integrated, to do a purposeful job, to run your cell phone? Tremendous, tremendous accomplishment. So we knew, this is 2003, I started working on the quantum dots in 1983. We knew that this was happening at that, and we knew they were getting smaller and smaller and smaller, the transistors. So intellectually, there was always a question, at some point, silicon would no longer behave like crystalline bulk silicon, just because the band structure was not fully developed. And so that was interesting. That was way off in the future, maybe 40 years in the future. But it was in the back of our minds. It was one of the reasons I worked on this. My work was accidental in this field. You know, I was 14 years out of graduate school before I began to work on colloids, metal colloids, and semiconductor colloids. I'd gone through a lot of different experiments. And I was working at that time on the surface photochemistry of colloidal semiconductors just because the area was so high. If you compare the area on the surface of small particles compared with the area of a bulk electrode, from signal to noise point of view, it makes better sense to work with a colloid. Copied these recipes out of the literature. And then noticed that, you know, sometimes the optical spectrum was changing. And this was traced to the growth of the particle size, Oswald ripening in the colloid. And so if you waited long enough, the particles grew, and then they had the bulk spectrum. But on the first day of making a colloid, sometimes the spectrum was blue shifted. Took a while to sort that out in my mind, you know, and all right. So now we come, so what's a quantum dot? Basically, we're talking about a particle, semiconductor particle, which maybe is 10 atoms across, 30 angstroms in diameter, 300, 400, 500 atoms. This is not silicon, obviously. This is a 2,6 semiconductor cadmium selenide, which we did a lot in those days. Maybe 1/3 of the atoms are on the surface, made by chemical synthesis. And I'll talk a little bit more about this later on. Reagents, molecular reagents, react together, correct temperature, correct solvent, correct coordinating ligands to make a particle in the liquid, and then capped by, this, in this case, trioctyl phosphine oxide. All right. So thinking about this, what were we trying to accomplish? Well, there's the intellectual or theoretical challenge, how to describe the electronic properties as a function of size. Ideas, models from physics, ideas from chemistry. There's a synthetic challenge. Can we actually make these things that we postulate on paper? That's more important by far. And can we vary the surface chemistry independently of the interior chemistry of the quantum dot? They have to be made well to be made useful, you know. And it's taken the quantum dots that are sold by Samsung 10, 15 years of work in an industrial laboratory to perfect the synthesis, you know, and to make it on a scale to be used in the televisions. And then because the synthesis is never really good, you know, you're talking, if you have something that has, say, 500 atoms in it, all of the quantum dots are not going to be exactly the same. They'll have a different atom here, a different atom there. And since the wave function extends over the entire particle, the wave function is sensitive to every atom. So that means that you need to measure these things one at a time rather than in the bulk, because to find out the real intrinsic properties. So this is to show that it really is a branch of chemistry. When you get down to the synthesis, here is a 3-neck flask with a solvent in the bottom and a septum. And you can inject with a syringe here, you can inject reagents, thermocouple, refluxing on the top here. And so you can, you know, you start with reagents, molecular reagents, which are colorless. And then as you begin to make semiconductor particles, at first they absorb in the blue, then the green, then the red. And so you can just follow with your eye the growth of the size as this thing is running. It was Moonji's hard work at MIT that perfected this synthesis that we use today. You could do sequential synthesis. You know, you can inject reagents to make, for example, cadmium selenide on the inside here, and then change the injection and add reagents to make cadmium sulfide instead. You know, switch sulfur for selenium. And if you do it slowly enough, You won't make any separate particles of cadmium sulfide, but you'll grow cadmium sulfide on the surface of the selenide, which is already there. So you make a core shell structure that has a higher band gap than, the sulfide has a higher band gap than the selenide. And you can put zinc sulfide on the south. So you can make out this whole series. You can make a core shell like this and cap the whole thing off with carboxylic acids or other ligands of this sort. So this is a powerful technique, because if you want to keep the electron in a hole away from the liquid, then you just need to put a higher band gap shell on the outside, and they'll penetrate less than they would without the shell. So let me go a little deeper now into the synthesis to show you what we struggled with in those days. And you see the names here of the people who worked on this with me. What we're doing today is not really a celebration for me. It's a celebration for the whole community of people back at that time, working together collaboratively. And you see the names here. As I said, none of this could have been done without this wide collaboration. I mean, the culture was such that, if you knocked on someone's door, they were more or less obligated to talk to you. But I mean, they were enthusiastic to talk with you. They could stop what they were doing and take 2 hours to talk to you about your problems, and you could learn very quickly that way. They were not obligated to actually work on your problems, but to give you advice and so forth. So that was just marvelous. I learned so much that way. So in the beginning, what we were doing was using inverse micelle solutions. This is a case where you have heptane solution and maybe 1% water, and it makes little droplets of water inside the heptane solution with soap on the interface like this. And then you could add reagents, and you could grow a small particle of the semiconductor inside this little water bubble. And it would be protected against fusion with the others by the micelle structure. So that was the first idea for how to control the growth. Stop at a certain size. And then we learned that these things were still reactive. So you could take one of these things and then stop, measure the optical spectra, and then add more reagents very slowly. And the molecular reagents could penetrate through the shell structure here, and then they would grow on the particle that was here, make a bigger particle of the same material. So it was reactive. I mean, much of this is the contribution of Mike Steigerwald, who is here today. So then we realized that you could do more exotic chemistry. So here on the top is, you make a particle, and then at the last stage, you inject a different molecular reagent that has a phenyl group as part of the reagent. And so what it does is it coats the surface with phenyl radicals bonded to the surface selenium atoms. That caps it in a molecular sense. It changes the particles from hydrophobic to hydrophilic, or vice versa, hydrophilic to hydrophobic. So if you do that, what happens is the particles just fall out of solution at that point. They make a powder on the bottom of the beaker, and you can purify this, and those are isolated and dry, purified quantum dots at this point of a certain size. But the quality is low, because it's a room temperature synthesis, and all kinds of defects and different sizes and shapes and so forth. Not perfect. But then we learned that you could take this stuff coming out of this synthesis, dry powder, and then reflux it in Lewis-based solvents like this, and it would grow better particles and larger. And here's the case where you reflux for 3 hours at 230 centigrade, tributylphosphine oxide solvent. It was Moonji who perfected all of this when he went to MIT. You can see the strength of Murray Hill down here. These are my collaborators. Pat Carroll's here today. We did all this fancy characterization work on these small particles through collaboration. TEM, powder X-ray, even, believe it or not, selenium-77 NMR, XAFs, cadmium and selenium XAFs. This works very well. I mean, when it's optimized, you know, it's kind of Edisonian to some extent, but when it's optimized, it works very well. This is an example from the laboratory of Chris Murray, who was at IBM at that time, showing you what you can make by this colloidal synthesis. And these are lead selenide nanocrystals. Look at the length scale here. So these are about 100 angstroms across. Here's the structure. So chemical synthesis is very powerful. But as I say, it has a certain Edisonian aspect to it. Now let me talk a little bit about quantum size effect and how one understands this quantum size effect. You know, there are equations in physics for the quantum size effect, and I could write those on the board, particle in a box and so forth. But I prefer to give this explanation, which is how a chemist would look at this problem, okay? The main important thing in a semiconductor or in a molecule is that chemical bonding is local. The most important thing is how the orbitals of one atom overlaps with the orbitals of the nearest neighbor, or, you know, and they can either be bonding or anti-bonding. So here's dicyanide, Si2H6, silicon-silicon bond, and then these other bonds to hydrogens here. And it's in a silicon crystal, it's the same. This is a tetrahedral arrangement here. It's the same tetrahedral arrangement here, 4 nearest neighbors, silicon-silicon bonds, except not just one of them. You have maybe 50 or 100 or 300, depending upon how big the crystal is. So this is how you would look at it from the chemistry point of view. So here's this red dot is a silicon atom, and here are 2 silicon atoms which are next to each other. So the p orbitals and the s orbitals overlap to form sp3 hybrids around each silicon atom, as Linus Pauling would have taught us. And then one silicon atom, the sp3 hybrids interact with the neighbor over here, and you can get a bonding overlap like this with no node, or you can get an anti-bonding overlap like this with a node running down the center. A bonding orbital, anti-bonding orbital, up from this energy right here, down or up. So this is Si2H6. Now, in a quantum dot, we have this same arrangement, except we have, as I say, maybe 100 or 300 of these local orbitals. And so these couple among themselves, and they make a series of molecular orbitals that are split out from the center of gravity right here. And this mathematics is known, you know, so that if you know the energy of this, you can predict how this family of bonding orbitals will split out and how the anti-bonding orbitals will split out like this. And so the asymptotic limit is, you know, you get 1 million orbitals, 10 million orbitals, you form the valence band, this continuous conduction band, which is continuous. This one is filled, that's empty. Bulk band gap here. But if you have a small particle, 30 nanometers, then you have a larger band gap, you know, homo-lumo gap. This one's slowly moving up like that. This one's slowly moving down like that. Band gap is larger. So the prediction is that you have discrete molecular states rather than continuous bands, and the lowest optical transition is larger. That's what the particles actually show. You can get exactly, so mathematically, it turns out this, this kind of picture of the orbitals in real space is mathematically equivalent to the phase space picture of the quantum particle in a box and so forth. And there's more to it than just that, you know. So you have to recognize that a particle like this has a high dielectric constant, maybe 10, and the outside environment, you know, has a low dielectric constant, maybe 1, or hydrocarbon-like. And so you have to take into account the ionization energies, the electrostatics of this problem, you know, and so you can solve this. This is an old problem in electrostatics textbook. I won't go into that. So you put this together, and you can make this simple model for what the band gap is of a small particle. And the advantage of this is that it's based on bulk, things which are known in the bulk. You don't have to guess. It's the effective mass of the electron, the effective mass of the hole, dielectric constant of the bulk, the radius of the particle, and you can predict, you know, the increase of the band gap of these different materials. And you can recognize you can make this kind of diagram for the physical size regimes of nanocrystals. As I have been saying, you know, at the small size, everything is molecular, and you don't really have this bonding of the same bonding as the bulk. Then there's a range of sizes where you get this quantum dot. The bonding sort of locks into the bulk bonding, but the size is not big enough to support continuous bands yet. And then you have quantum dots. You get really big. You get down to the diameter equal to the wavelength of light, and you have shape resonances, polariton effects, and so forth. All of these exist as a particle grows larger and larger. So let me take a minute now and talk more generally about nanoscience. This quantum size effect is just one aspect of what's going on in nanoscience, and perhaps the simplest aspect. It's a single electron property. It's not involving correlation. But there are other nanosystems, carbon nanotubes in particular, graphene, that show a very strong electron correlation. I'll say a little bit about that. The other thing that's going on is that as an object gets, you know, there are two types of interaction with the electromagnetic field. There's absorption and luminescence, as you would ordinarily see. There's also Rayleigh scattering. Rayleigh scattering is negligible for most small molecules, but Rayleigh scattering increases as the square of the number of atoms, roughly, and absorption luminescence is linear with the number of atoms. So if some object gets larger, the Rayleigh scattering can become significant and even dominant. So you can characterize these things using the coherent Rayleigh scattering, as well as absorption and luminescence. And all of these things can be worked out. We've done a lot with carbon nanotubes. This is a very interesting system. You know, so this is a short segment. You can imagine a nanotube like this running to infinity backwards and backwards. This is kind of hybrid solid state with the quantum size effect added on. If you have an electron which is going around the circumference like this, the electron has to positively interfere with itself as it comes back around to the original position. This is a periodic boundary condition that leads to quantization of the energies of those electrons. But electrons running down the entire length of the tube like this, just see infinite crystalline structure. They show band structure. So electrons will propagate down a tube like this, but in different transverse modes. A little bit like an optical fiber. You know, optical fiber, light goes down the tube. You have different modes having to do with what's happening along the perpendicular to the length. Same thing in the carbon nanotube. In Murray Hill here, I worked some with Stefan Schmidt-Rink back at this time. He was a theorist in the theory department, I guess, you know, and I think he was the first one to point out, and Mark Harbison pointed this out to me, the extreme role of dimensionality in all of these issues. And so, you know, a good comparison is like confinement. You can confine let me back off a little bit here. Confine an electron in a hole in a three-dimensional semiconductor. And so you have an exciton, you know, electron and a hole form an orbiting pair. They attract each other, a little bit like a hydrogen atom. That can happen in 3 dimensions, or it can happen in 2 dimensions, depending on the structure. But there's a profound shift in the balance between the kinetic energy and the potential energy, going from 3 to 2. Basically, in 3 dimensions, it's very easy for electrons to avoid each other, repulsive interaction. But in 2 dimensions, it's much harder for the electrons to avoid each other. And in 1 dimension, it's actually divergent. You know, if electrons are moving up and down a line like this, they unavoidably collide with each other. So you put that together, you get this very strong electron correlation in pure dimensionality effect. There's also decreased screening. Let me show an example of that. Carbon nanotube, infinite carbon nanotube, for example, has a higher dielectric constant. Outside you have vacuum. So if you have an electron and a hole close to each other, it's partially screened. It's screened by the dielectric constant of the nanotube itself. There's some fringing of the field outside into the vacuum where there's no screening. If, in fact, they're further apart, a greater fraction of the field goes out like this. In the case where they get really far apart, there's no screening because the electric field is outside entirely. So there's a Coulomb interaction between the electron and the hole, but it deviates from the Coulomb interaction because the screening depends upon the separation, like this. This has all been worked out in carbon nanotubes. It's one aspect of what nanoscience going on in this. All right. So I'm coming to the end here. In quantum dots, we have simple quantum confinement, but these particles, when you make them well, are new classes of large molecules. They're excellent chromophores. Carbon nanotubes are superb molecular wires. The most important thing in nanoscience is not this theory, but it is, in fact, the ability to make these structures and to put them where you want them, to make them in a place where you want them, actually. It's the same problem involved in the manufacture of chips. So I'm profoundly grateful to Bell Labs because, as I have said, it was a great place to work when I was here. And I made so many friends and learned so much from all of the people who are sitting here in the room today. At Columbia, it's been similar, actually, because I've had some strong collaborations with Tony Heinz, Dave Reichman, Philip Kim, and with the students in my group. So there was a time I went to Singapore, I think it was, and had to give a talk to a large group of, I had to give a talk in a symposium, and on Saturday, the last day of the meeting, they told me I had to give a talk to a room full of high school students about how to become a good scientist. And so I had to go home Friday night and write this down, what you see on the board here. We're all trapped by our educational backgrounds. And to change this, you need to learn something new every day. That's the greatest skill we have. What are your colleagues working on? Why is it important? So that was very easy here in Bell Labs because I could just ask them what they were working on, and then they would explain to me why they thought it was interesting. May not be interesting to me, but I would learn something in the exchange between going back and forth like that. In my life, I've always been searching for a better problem. As I said, I was 12 years out of grad school, had worked on a number of things before I stumbled into this work on colloidal metals and colloidal semiconductors. This work, particularly on the border between chemistry and physics, is an example of what I've been saying here. So I thank you for your attention, and thank you for coming today.